The next set of lectures that we're going to look at tries to do much of the same sort of thing that we did previously with recognizing the two-dimensional flat shapes, except for instead of rigid shapes, now we're going to deal with deforming shapes. This is again a technique which can be generalized into three-dimensional type data, but we're just going to deal with the simple version that deals with two-dimensional data. So imagine that you have a class of shapes. Okay, here we've got a set of t's. We've got t's that come in, as well as all positions, they come in a variety of shapes and sizes. Here's a sort of a short stem, here's a very thin, sort of thin head on it, maybe here's a bit of squint or whatever kind of bit on the T, the stem of the T. So this is a set of variations, and what we would like to be able to do is really two things. One is to somehow encode all of the variation that we normally find in this family of shapes. And the second thing is we would like to be able to recognize instances of that shape and say, well, this is a shape which sort of fits this family of shapes pretty well. It's part of similar to the training data, or to be able to reject it and say, oh, this is a shape which doesn't really look like anything that we've seen before. So the problem is, really, how do we want to represent all of those shapes in that class? And then once we've got that representation, how can we use the statistics of that shape to be able to determine whether the new sample that we've got, the new object that we're looking at, is one of those shapes or whether it's a different sort of shape. So that's what we're going to be looking at, as we're going to look at effectively deformable part type modeling. So we're going to look at a technique for representing those parts, and then we're going to have to look at techniques for modeling the shape distribution. So there's really the three stages. One is we're going to have to look at ways to orient all of these shapes into a standard position. Then we're going to build our point distribution models. We'll talk a bit more about what those are in a minute. And then we're going to look at recognizing the objects by looking at the probability that the shape fits that distribution. In order to do all of that, we're going to use a lot of the technology that we've used previously. We're going to have dark parts against a light background. We're going to threshold them as we did previously. We're going to track around the boundary. We're going to segment that boundary into straight line segments. Although in this case we're going to do it a little bit more accurately than we did with the rigid parts that we saw previously. Well, why do we want to do that? Well, there's lots of objects that we're interested in that come as a kind of a family. Okay, and this may be either when we're looking at natural objects or we're looking at manufactured objects that have some sort of natural variation. So here's an example. We've got a whole bunch of loaves of bread which are coming down a production line. And although a lot of the production process tries to make each loaf of bread be as similar as to every other loaf of bread, there's still going to be natural variation. The corrugations on the top, slightly different in sizes and shapes and things like that. So we'd like to be able to build a model which says this is what a good loaf of bread looks like, but allow some kind of a tolerance in there. Similarly, hams come in different shapes and they also come in different positions, okay, if you change the joints around. Here's another, bananas. You would all recognize a banana instantly, but they have different shapes and sizes as well too. And we'd like to have some kind of model that can account for all that variation in a natural sort of way. Here we're going to be focusing on just a single shape. Okay, this is going to be a T shape. Okay, it's going to be our dark T against a lighter background, and there's going to be a whole bunch of variations. Here are some examples of those shapes. What we would like to do is identify the common modes in those shapes, and that in this case what that means is the standard ways in which those shapes can vary. And we'd also like to represent those standard ways in some sort of statistical form. And then finally we would like to be able to recognize those objects given those statistics. In order to do all of that, we've got quite a long sequence of steps that we're going to have to deal with. The first, we're going to start with the principal component analysis. This is a standard technique in quite a lot of computer vision type applications at the moment, and so therefore we're going to have a little bit of a review of that, a little bit of an introduction to the topic area. The core algorithm we're going to be looking at is what's called the point distribution model, and we're going to look at how we can use the principal component analysis to build these point distribution models. Once we have the models, we can then look at algorithms for learning those models and using those models to classify the data. As I've said previously, a lot of our algorithms are quite straightforward. The point distribution model is actually pretty simple, but to get our data to the point where we can use that point distribution model is a bit more of a complicated sort of thing, and it actually is very much problem dependent. So in our case, we're going to have to somehow rotate our t's into a standard position. That's going to be a bit heuristic. Once we've got the t's in the standard position, then we can build our point distribution models, and then we can do our classification. Thank you.